As you can see, this is joint work with George Monette from York University in Toronto. George had hoped to be here, but had to cancel. And we had planned to do this talk tag team style, that is, each to do part of the presentation. But unfortunately now, you're stuck only with me. Okay, so I'm not sure whether everyone here is familiar with regression splines. So there will be some elementary material here which links up with what George and I have done. But very briefly, regression splines are piecewise polynomials that are constrained to join smoothly at connection points, which are called knots. And regression splines feature prominently in a number of texts on applied regression analysis. One of them is my text, and another, even more prominently, is Frank Harrell's very nice book on regression modeling strategies. Regression splines have several advantages relative to other ways of handling nonlinearity in regression models. For example, in comparison with power transformations like the Box-Cox family, including the log transformation, regression splines can deal with relationships that aren't simple or that are non-monotone. Another more traditional way of dealing with nonlinearity in parametric regression models is by polynomials, like quadratics and cubics. But polynomials are highly non-local in that the data at one point in the predictor space can seriously affect, substantially affect the fit at another point in the predictor space. Unlike non-parametric regression, regression splines are fully parametric so that they can be incorporated in relatively simple regression models like linear models, generalized linear models, and linear and generalized linear mixed effects models, among others. As you'll see, our implementation of regression splines will work anywhere in R where you can specify a linear model-like formula. Okay. Usually, however, in developing regression splines, the focus is not on the parameters that are being estimated, but rather on the shape of the fitted regression function or partial regression function. And that's entirely reasonable, but on the other hand, it represents a kind of lost opportunity, because the parametric nature of regression splines, for example, makes it easy to makes it possible to estimate quantities of interest and, for example, to test hypotheses about them. For example, about transitions. I won't be able to fully explain how our approach to generalized regression splines enables those characteristics because of lack of time. And in fact, I'm going to be able to essentially expose only, I would say, about 25 or 30% of what we've done. Okay, so we've implemented what we called generalized regression splines using the GSP spline function in the CARX package. CARX is CAR experimental or CAR extensions. The CAR package is associated with Sandy Weisberg in my book, Companion to Applied Regression, and is a package that's available on CRAN and fairly widely used. Eventually, the material that I'm talking about today will move from the CARX package to the CAR package. Okay, I'm going to talk about several things. I'll try to explain what regression splines are about for people who haven't seen them before, but also as a way of explaining how George and I have extended regression splines to produce generalized regression splines. I'll explain how these are implemented, at least at a basic level, not all the features, in the GS Spline function. The next part of the presentation we've left in the slides because it's of theoretical interest, but I'm actually not going to present it, both because of lack of time and because the linear algebra is intricate, and I don't think it's really an appropriate topic for this context. But we've left some of this material in the slides so you can see how this works. And there's even more material in the CarX package in a couple of vignettes. I'll show you an illustrative application to data on unemployment rates in Canada, including the period of the financial crisis in 2008. And finally, assuming that I get to it, I'll explain some of the other things that we have in mind for implementing generalized regression splines. Okay, if you want to try this out for yourself, the CarX package isn't on CRAN, but it is on RForge. So you can install it from RForge. Okay, so to have a point of reference to create a simple example, I've generated some data where the explanatory variable x is sampled from a uniform distribution between 0 and 10, and where random errors are sampled from a normal distribution with a mean of 0 and a standard deviation of 0.5. And the regression function combines a trigonometric term with a linear trend, okay, plus error. So that the mean function is that we would essentially trying to capture is a trigonometric function plus a trend. And at the right, you can see the data and the graphed true mean function. Okay, so I'll introduce a series of successively more complex segmented polynomial regression models and spline models. And the final model will be a traditional cubic regression spline. Okay, so starting with piecewise polynomials, we'll carve X into a number of non-overlapping regions at several knots. And within each region, we'll fit a degree P polynomial, initially unconstrained. So, for example, here's the simplest case where the degree of the polynomial is 0 so that we have a piecewise constant fit. I mean, clearly that doesn't do a very good job of capturing these data. In effect, we're simply fitting a mean within each interval, the intervals defined by the knots. Here I've set the knots at the 1/3 and 2/3 quantiles of the distribution of X. Okay, here's a next step where I fit degree 1 polynomials, that is, lines within each of the regions defined by the knots, again unconstrained. And finally, in this sequence, we can turn the piecewise linear fit into a linear regression spline by constraining the lines to join at the knots. Okay, so how can we do that in a linear model? There are various ways of creating spline bases for a model like that, but here's a particularly simple one, defining 3 regressors, x1, x2, and x3. x1 is simply the explanatory variable x. x2 is x minus the first knot to the right of the first knot, and 0 at and below the first knot. X3 is similar except above the second knot. And other than that, we would simply fit this by least squares. Okay. Coding this in R is very easy. And the coefficients of the model have simple interpretations. Beta hat 0 is the expected response at x equals 0. Beta hat 1 is the slope in the first region. Beta hat 2 is the change in slope at the first knot, and beta hat 3 is the change in slope at the second knot. Okay, so our goal is to have similar simplicity in higher degree and other more complex regression models. So here's the generalization of this, for example, to a cubic regression spline, where by suppressing the linear and square terms in the second and third interval, we cause the first and second derivatives, the slope and curvature, to match on both sides of each knot. Again, this is very straightforward. Okay, in the GS spline function, we generalize this idea to be able to fit models that can't be fit by coding regressors as simply in the examples that I've shown you just thus far. In fact, I'm going to, as I said, expose only a fraction of what G-spline can do. Okay, so there are several arguments to G-spline. The first argument is required, which is the knots argument, specifying the location of the knots. There's a degree argument, which either could be the degree overall or the degree within each interval. There's a smoothness argument, which can either be the number of derivatives matched everywhere or the number of derivatives matched at each knot. So we allow the possibility of different degrees of continuity at different knots, and also different order polynomial fits in each region. G-spline returns a function, that is a closure, which one can then use within a linear model formula. The closure has several arguments, only the first of which is required, x. X would, in specifying a model, be an explanatory variable for which we want to create a spline, but x could also be a variable that generates an hypothesis matrix concerning the parameters estimated for the spline. So here's how we would do the various spline fits that I've already showed you, and some more using G-spline. Okay, so the piecewise constant fit, a piecewise linear fit, where smoothness of -1 indicates a discontinuity, a linear regression spline with smoothness 0, that is matching level but nothing else at each knot, a piecewise cubic fit, and a cubic regression spline with only continuity, not matching any derivatives. A cubic regression spline with matching slopes, and a cubic regression spline with matching slopes and curvature. Okay, it's also possible to create natural splines using G-spline. I'll pass over that and move to an example. So I have here monthly Canadian unemployment data from January 1995 to February 2019. Okay, the data are percentage unemployment rate. And here is a picture of the time series. And you can see that there seems to be a jump in December of 2008. That's when the financial crisis hit Canada. I'm going to create knots at the quintiles of the explanatory variable here, which is time, that is year, and add a knot at what we take to be the date of the financial crisis, which is mid-December 2008. And then I'm defining and fitting several quadratic and cubic spline models with and without a discontinuity at the date of the crash. You can see that we call gspline to create a spline generating function, and then incorporate that on the right-hand side of the linear model formulas. So here's a quadratic regression spline, a cubic regression spline, a discontinuous quadratic, a discontinuous cubic. Okay. Now, the data also have a periodic character, which we've not yet captured. And it's possible to define what we call periodic splines, which essentially wrap around at a boundary knot, allowing continuity at both ends. And here we add an annual periodic spline to the discontinuous cubic spline, and apparently are able to capture the data better. Quick model comparison, the last model, which has both a continuity and a periodic component, is greatly preferred by the AIC. Okay. Very briefly, what we intend to do is to try to, when we know how actually, but have not yet implemented it, to make these regression splines more numerically stable. And the trick is to essentially orthogonalize them, but to save the information about the orthogonalizing transformation, orthonormalizing actually transformation, so that we can back transform to estimate parameters of interest.
Okay. Thank you very much, John. Time is always too short. We have time for one very important question.
What about penalization on the estimation? How would that play together with this approach best?
I'm just repeating the question for the recording. So the question was how penalization takes place in this
Well, a penalized spline would be more like a non-parametric regression. I frankly haven't thought about that. Yes. I mean, we are, when we're looking at the AIC, we're penalizing in a sense, but it's not incorporated in the estimation. If you have ideas how to do that, I mean, our code and the math is there. We'd certainly be interested in the possibility of extending it.
Thank you very much, John.